All right, now in problem 3, we'll look to do the reverse. So we're going to start with rectangular coordinates and convert them into polar coordinates. So this time I've highlighted the second two equations in that box. So I was using mostly x equals r cosine theta and y equals r sine theta when I wanted to convert from polar to rectangular coordinates. So if I want to go in the reverse direction, I want the second two set of equations. And they're equations that we already know. Tangent theta equals y over x is the same as tangent is equal to opposite over adjacent. We've been doing that since unit 3 or worksheet 3. And that other equation, r squared equals x squared plus y squared, that's simply the Pythagorean theorem with some different labels on it. Instead of a, b, and c, we have x, y, and r. So we'll just use those equations to convert rectangular coordinates into polar coordinates. So let's start by getting r. So if r squared is going to be equal to x squared plus y squared, that means in this particular case that r squared is equal to 16. So that'll be 8 plus 8. So we'll hold off for just a moment before we figure out exactly what r is going to be. And we'll take a look at theta. And theta should be, or at least the reference angle for theta, should be equal to, let's make an edit here. So we also know that the tangent of theta should be equal to y over x. So 2 root 2 over 2 root 2, which upon simplifying is 1. So I have a number of different options for theta here. So it's going to be important to pick one of the correct ones. Looking back up at our point, both x and y are positive, so we should be in quadrant 1. So picking an angle in quadrant 1, I can probably use theta equals pi over 4, since that angle will put us in quadrant 1. And if I'm using pi over 4 as my angle, then r should be a positive value. So I want the point 4 pi over 4. And that'll be my coordinate, my polar coordinate. And then looking at part B, we'll get that same setup going. R squared is equal to negative 1 squared plus root 3 squared, which means r is 1 plus 3, which is 4. So again, we'll end up with r could be either positive or negative 2. We'll go do that same thing where we say that tan theta should be equal to y over x. So root 3 over negative 1, or just negative square root 3. Which means then I'd have a couple of options for theta, right? Because either theta could be negative 2 pi over, nope, not negative 2 pi over 3, just positive 2 pi over 3, right? So something over in the second quadrant. So 2 pi over 3 would be fine for theta. Or if I actually take the tangent inverse here, I would get negative pi over 3, also a valid angle. Additionally, if I wanted to stay within the unit circle, I could also use 5 pi over 3. Any one of those 3 angles would work for theta. We just have to decide which one we want. So looking back up at the point, we have a negative x value and a positive y value, which means we're in quadrant 2. So if we want to keep using a positive value for r, I'm going to need to pick an angle that is in quadrant 2, which means that for my angle, I'll choose 2 pi over 3. Since that'll keep us in quadrant 2. Meaning then that the point I've chosen to go with should be positive 2 for r and 2 pi over 3 for theta. But it wasn't until I chose my value for theta that I knew if r would be positive or negative. All right, on to points C and D. So it looks like this time we have r squared is equal to 4 root 3 squared plus negative 4 squared, which simplifies to 3 times 16 plus 1 times 16 would be 4 times 16 or 64. So r could be either positive or negative 8. Then we'll look at theta. And we start by only really having that tangent of theta is equal to negative 4 over 4 root 3, since it's equal to y over x. And that simplifies to negative root 3 over 3. So a few options for theta. Since it's negative, if I just took the tangent inverse of negative root 3 over 3, I would get negative pi over 6. But other options on the unit circle would be 5 pi over 6 or 11 pi over 6, since both of those would give a negative tangent value. So let's come back up and look at our xy point, where we have a positive x value but a negative y value, which puts us in quadrant 4. So if I again want to keep working with positive values for r, I'll need to choose an angle that's in the 4th quadrant, which means either negative pi over 6 or 11 pi over 6. Let's stay within the unit circle, just between 0 and 2 pi, so we'll choose 11 pi over 6. And so it's because of my choice of theta being 11 pi over 6 that I can then say that I'm going to take the positive value for r. So r is 8, while theta is 11 pi over 6. On to part D. Here I've got that r squared is equal to negative 3 squared plus negative 3 squared, which works out to 18, meaning that r is plus or minus 3 times the square root of 2. So it didn't come out to an integer this time, but that's okay. So a couple choices for r. So we'll look at our choices for theta. Tangent of theta is equal to negative 3 over negative 3, which is 1. So theta, I get a couple of options. I could either go with pi over 4 in the 1st quadrant or 5 pi over 4 in the 3rd quadrant. So if we come back and look at our original xy point, I have both x and y are negative, which means we're in quadrant 3. So to keep a positive r value, not that a positive r value is necessary, but it is usually nicer to work with a positive r value, I'm going to choose an angle that is in the 3rd quadrant. So instead of pi over 4, which would work for theta, I'm going to choose 5 pi over 4. And since I chose that point, I should have a positive value on r. So my coordinate point, my polar coordinate works out to 3 root 2 for r and 5 pi over 4 for theta. And then in problem 4, I will be converting rectangular equations into polar form. So as much as we can, we'll look to simplify these equations. So anytime we've got an x squared and a y squared, we'll try to add them together to get r squared. And anytime we've got x or y by themselves, then we'll try to do something like plug in an r cosine theta for x or an r sine theta for y. So in that first one, in part A, the first step I'll take is to move that x squared over to the other side so that I'll have x squared plus y squared is equal to 5x. And then in this step, I'll make some substitutions. So x squared plus y squared I know is equal to r squared. On the other side, I know that x, if I have just x by itself, that should be r times cosine theta. And I'd probably be fine to leave the equation here, but I'm going to simplify this one step further since I have an r on each side and just reduce to say that r is equal to 5 cosine theta. Then on to the other side, I have that x squared is equal to 1 minus y squared. That would be the same as x squared plus y squared is equal to 1. So I have the equation r squared equals 1. And now r squared equals 1 means that whatever distance I am away from the origin, it's a distance of 1 away. But in polar coordinates, there is no real distinction between r equals 1 and r equals negative 1 because they both talk about the same circle. Whether r is positive 1 or negative 1, it just means that r is a distance of 1 away from the origin. So I'll use r equals 1 as the equation of this circle. And again, that should just be the unit circle, since we know that in the unit circle, x squared plus y squared is equal to 1. All right, on to parts C and D. So we'll gather our y squared on the other side. So x squared plus y squared is equal to 7y, meaning r squared is equal to 7 times y, which would be r sine theta. And I'll also just simplify that one more step like I did that first time. Say that r is equal to 7 sine theta. All right, and then part D, got a bit of an interesting equation going on. I've got y equals the square root of 3 times x. And probably the easiest way here, since neither piece is squared, would be to just substitute directly in for y and x. So y, we know, is r sine theta. And that's going to be equal to the square root of 3 times r cosine theta. And then I'll start working to simplify. If I divide r cosine theta over to the left side, first those r's are going to reduce, but also I'll get sine theta over cosine theta is equal to square root of 3. Then that equation simplifies as well. I know that sine over cosine is equal to tangent of theta. And now finally, I could solve this directly for theta. So theta should be equal to the inverse tangent of square root of 3, which is pi over 3. So in the end, I get kind of an interesting result here. I started with the equation y equals the square root of 3 times x, which from algebra, we know that that's just y equals mx plus b, where m is the square root of 3 and b is 0. So I started with the equation of just a line, and this line happens to have a slope of the square root of 3. And after solving that, I get the polar equation theta equals pi over 3, which means that anytime I have a polar equation that's simply theta equals some number, that's talking about just a straight line, just a linear equation like we would have in rectangular coordinates, which is a bit of an interesting result. So again, bottom line there, if we have the polar equation theta equals something, that's just describing a linear equation. And finally, part 5, we're going to go the reverse direction. Convert from polar coordinates to rectangular coordinates. So these problems tend to be a little on the trickier side, so let's go through some of them. One thing I like to do is anytime I have an r by itself, so just r hanging out with no sine or cosine on it, I'll usually multiply both sides by r. Additionally, that'll work out well because I have a sine theta hanging out by itself. It'd be nice if I had r sine theta so I could substitute y in directly. So again, multiply both sides of this equation by r to get r squared is equal to negative 6 r sine theta. And now I can convert these pieces directly into rectangular coordinates. So r squared is just x squared plus y squared. That part's not too bad. And on the left, I have this r sine theta, which I know should be just y. So x squared plus y squared equals negative 6y. On to part B, I have theta equals 7 pi over 6. So I'll take the tangent of both sides and have the tangent of theta is equal to the tangent of 7 pi over 6. And then I can actually get a number there. Tangent of 7 pi over 6 is square root of 3 over 3. And it's positive because we're in the third quadrant. So then I'll just change tangent to y over x. So y over x is equal to the square root of 3 over 3. So 3y is equal to square root of 3x. Or if I wanted that more in a y equals format, I could have just left the root 3 over 3 all on the right side and had just y equals root 3 over 3x. Okay, part C, I again have an r by itself. But this time I just have r equals a number, whereas in part A, I had an r by itself and a sine by itself. So in that case, I decided to multiply both sides by r. This time, since I just have r equals a number, that means I'm talking about the circle that has a radius of 4, right? R equals 4, radius of 4. And the center of this circle would be the origin. So I just want to describe that equation in rectangular coordinates. So this time, instead of multiplying r to both sides, I'll just square both sides. So this time I will get r squared equals 16, which gives us the equation x squared plus y squared equals 16. So if you're familiar with rectangular equations for circles, you might remember that the general equation for a circle is x squared plus y squared equals the radius squared. And that's only if we're talking about circles centered at the origin. But finally, part D. Here again, we have an r by itself, but we also have a sine with no r attached to it and a cosine with no r attached to it. So I'll again multiply each of these things by r. So 2r sine theta minus 3r cosine theta is equal to 6r squared. And then I can make substitutions for each of those pieces. 2y minus 3x is equal to 6 times x squared plus y squared. And that would be our equation in rectangular coordinates.